The first sign was not collapse, but silence. Deep underground, in shafts carved by iron teeth and steam-driven drills, the rhythm of digging simply stopped. No warning cry reached the surface. No tremor announced the failure. Only the absence of sound, as if the earth itself had swallowed its own breath. We were not meant to go this far beneath the world, but the machines demanded depth. Steam-powered boring heads, reinforced iron cages, and cable-hoisted lifts pushed workers further into stone than any hand-dug shaft had ever reached. What began as extraction became intrusion, and what was once labor became descent into something the earth had kept sealed for centuries. It was called a machine only in the language of progress. In practice, it was a burrowing system of steel and steam, driven by engines that never learned caution. It chewed through layers of shale and coal seam, then deeper still, until air itself began to change. Workers spoke of foul breath rising from the rock, of lamps dimming without reason, of passages that seemed to exhale rather than hold still. Then came the finding that could not be mapped. Chambers that were not natural, but not built either. Voids lined with pressure-warped stone and air that killed without touch. When the machine dug too deep, it did not uncover treasure or seam alone. It uncovered conditions that should not have existed at all. And every attempt to measure them only confirmed a single truth. The deeper it went, the less the earth resisted, and the more it revealed something waiting beneath it. A question remained unanswered in every report. Was the machine discovering the earth, or awakening what had been buried for a reason? Before the machine ever descended into the earth, excavation was not a conquest. It was negotiation. A slow and uncertain agreement between human strength and the resistance of soil. Stone and depth. The earliest miners did not dig deep. They could not. The earth, in its upper layers, yielded reluctantly, but beyond a certain point, it became something else entirely. Denser, heavier, more unpredictable. Every additional meter brought new risks that no tool of the time could fully solve. Work began at the surface, where ore veins sometimes revealed themselves through erosion or broken rock. Men followed these veins inward using hand tools, iron picks, wooden shovels, baskets for hauling material. The tunnels they created were narrow, shaped not by engineering design, but by the limits of what a human body could physically carve and sustain. There was no certainty of direction, no mapped system beneath the ground, only instinct, observation, and repetition. A vein might continue for meters or vanish without warning. A promising seam of ore could collapse into worthless stone within a single day's work. This uncertainty defined everything. As demand for coal, tin, copper, and iron increased across Europe, surface deposits began to decline. What remained required deeper extraction, but depth introduced conditions that early mining systems were not built to survive. Air, first of all, became a problem. At shallow levels, ventilation occurred naturally through shafts open to the surface. But as tunnels extended downward and outward, airflow weakened. Stagnant pockets formed. Candles flickered and dimmed. Workers learned to recognize bad air not by instruments, but by senecture, tightness in the chest, dizziness, an invisible heaviness that made each movement more difficult than the last. They called it foul air, though they did not yet understand its composition. What accumulated in these depths was a mixture of carbon dioxide, methane, and other gases released from decomposing organic material and geological pressure. In confined spaces, these gases displaced oxygen silently. A miner could collapse without warning, and often there would be no recovery. Then there was water. As shafts deepened, they began to intersect underground streams and aquifers. Water seeped through rock fractures, pooling in low areas, flooding tunnels faster than it could be removed. Early pumping systems were primitive: manual buckets, animal-driven mechanisms, or rudimentary water wheels. None of them could match the scale of infiltration at greater depths. Some mines were abandoned, not because they ran out of ore, but because they filled with water faster than they could be drained. Collapse was another constant threat. The deeper the excavation, the greater the pressure exerted by surrounding rock. Wooden supports were installed to reinforce tunnels, but timber degraded over time, weakened by moisture and strain. A single failure could trigger a chain reaction. One beam collapsing would shift weight onto another, and then another, until entire sections of the mine gave way. When this happened underground, there was no escape, only silence after impact. Explosions added a further dimension of danger. Methane, released naturally in coal seams, accumulated in pockets within mines. When exposed to flame, often from open lamps or sparks, it ignited violently. The resulting explosions tore through tunnels, consuming oxygen and collapsing structural supports. Survivors described it not as fire, but as a sudden absence followed by destruction. Despite these dangers, demand for raw materials continued to rise. Agriculture required stronger tools. Construction demanded more durable materials. Early industry required fuel. Every expansion of society increased pressure on mining systems that were already operating at the edge of human capability. The contradiction was absolute. The deeper resources existed, the more they were needed. Yet the deeper they were pursued, the more dangerous extraction became. Work was organized in shifts, but those shifts were dictated less by safety than by necessity. Miners worked in darkness, illuminated only by dim, unstable light sources. Time underground was measured not by clock, but by fatigue, by air quality, by the physical limits of endurance. Children were sometimes employed in these environments, not because it was safe, but because their size allowed them to move through narrow passages adults could not access. Their presence underscores the system's reliance on bodies rather than technology. Human form adapted to conditions no machine yet controlled. The tools themselves reflected limitation. Pickaxes, chisels, and shovels remained the primary means of extraction. Each strike removed only small amounts of material. Progress was measured in inches, sometimes fractions of inches when rock density increased. There was no acceleration, only repetition. Transport within mines was equally primitive. Ore was carried in baskets or wheeled in carts along wooden tracks. These carts were heavy, unstable, and difficult to maneuver in confined spaces. Accidents were common. A single derailment could block an entire passage or injure multiple workers. Despite these constraints, mining expanded, not because conditions improved, but because demand outpaced risk. Entire regions became dependent on extraction economies. Villages formed around mine entrances. Generations of families entered the same tunnels, inheriting both employment and danger. Mining was not an occupation chosen freely in many cases. It was an economic condition that defined survival. Attempts were made to improve efficiency. Water drainage systems were enhanced using early steam engines, which provided more consistent pumping power than manual methods. Ventilation shafts were extended and connected to surface airflow systems. Structural supports were improved with better timber and later, early iron reinforcements. But these changes were incremental. They did not solve the fundamental problem. The deeper the mine extended, the more unstable it became. Engineers began to recognize that the issue was not simply one of tools or labor, but of scale. Human systems could not reliably operate at extreme depth without introducing exponential risk. Each additional layer of excavation added complexity not just to extraction, but to survival. Yet the pressure to dig deeper did not slow. Surface deposits were becoming scarce. Industrial expansion required more fuel and material. Entire economies were built on the assumption that resources below ground were effectively limitless, if only they could be reached. This assumption drove innovation forward, but also masked the cost. Geological surveys of the time were limited. Understanding of subsurface conditions was incomplete. Miners often worked blindly, guided by experience rather than accurate mapping. Unexpected voids, unstable rock formations, and sudden gas pockets were discovered only when encountered directly. Every new depth represented both opportunity and uncertainty. And uncertainty, underground, was not abstract. It was structural. It determined whether a tunnel would hold or collapse, whether air would remain breathable or become toxic, whether a passage would remain open or seal itself without warning. As mines expanded, so did the need for a system capable of operating beyond these constraints. Not just stronger tools, not just deeper shafts, but a mechanism capable of maintaining stability in environments where human judgment and physical endurance were no longer sufficient. The problem was no longer simply extraction. It was control. Control over depth, control over air, control over collapse, control over conditions that resisted prediction. At the edge of this limitation, the idea began to form, slowly, unevenly, that excavation itself might require transformation, that digging deeper would not be enough, that something else would need to enter the earth in place of human labor, capable of sustaining pressure, maintaining direction, and continuing where human bodies could not safely remain. The machine, when it eventually arrived, would not simply extend mining capability. It would redefine it. But before that transformation could occur, the limits of the old system had to be fully reached. And beneath those limits, deep in the narrow, unstable tunnels carved by hand, the earth continued to resist every attempt to be fully known. The idea of digging deeper than human bodies could safely endure did not begin as a single invention. It began as a pattern of failures accumulating across mining regions, each one exposing the same truth in different conditions. The earth did not yield uniformly, and every attempt to force it did so at a cost that scaled faster than the reward. In the late 18th century, mining districts in Britain, Prussia, and parts of France were already reaching depths that traditional hand-dug systems could not reliably sustain. Shaft collapses were increasing. Flooding events were becoming more frequent. Ventilation failures were no longer isolated incidents, but recurring structural weaknesses in the entire system of extraction. Industrial demand, however, did not slow. It accelerated. Coal was no longer just a resource for heating. It had become the foundational fuel of steam engines, factories, and early transport systems. Iron production depended on it. Entire cities were powered by it indirectly. As industrialization expanded, the demand for deeper and more consistent extraction intensified. This pressure forced a shift in thinking. Mining could no longer be treated as a manual extension of surface labor. It required mechanical intervention at depth. Early attempts at mechanization were indirect. Steam engines were introduced at the surface, primarily to pump water out of flooded shafts. These engines, developed and refined by engineers such as Thomas Newcomen and later James Watt, did not enter the mine itself. They operated above ground, connected through rod systems that transferred motion downward. This was the first structural separation between human labor underground and mechanical power above it. But even this solution revealed limitations. Pumping water solved one problem while exposing another. As mines were drained more effectively, workers were able to dig deeper, which led to increased encounters with unstable geological layers and hazardous gas pockets. Mechanical improvement expanded access, but also expanded risk exposure. The system was not stabilizing. It was escalating. By the early 19th century, mining engineers and industrial investors began to consider a more direct solution, a machine that could operate within the mine itself, not just support it from above. This idea emerged alongside broader developments in mechanical engineering. The Industrial Revolution had already demonstrated that continuous motion, powered by steam, could replace intermittent human labor in factories. Textile machinery, ironworking equipment, and transport systems were all being transformed by centralized power sources. The question became whether excavation could undergo the same transformation. In regions such as Cornwall, where deep mining had already pushed into difficult geological zones, experimentation intensified. Engineers like Richard Trevithick, who worked extensively with high-pressure steam systems, explored the possibility of using steam-powered mechanisms in more mobile applications. Early prototypes were not fully subterranean machines in the modern sense. They were hybrid systems, mechanical frameworks designed to assist excavation, stabilize shafts, and reduce direct human exposure to the most dangerous tasks. But these early systems revealed both promise and limitation. Steam power could generate sustained force, but it required fuel, water, and maintenance. Early mechanical components were large, heavy, and difficult to deploy in confined underground spaces. The deeper the mine, the more difficult it became to deliver and operate machinery effectively. Still, the trajectory had changed. Mining was no longer viewed purely as manual extraction. It was becoming a mechanical problem. At the same time, industrial geology was developing as a field of study. Engineers and surveyors began to map subterranean formations with increasing precision. They identified coal seams, ore veins, and structural layers not as isolated resources, but as part of continuous geological systems. This knowledge reinforced a dangerous assumption that depth itself could be systematically controlled. Investment in mining infrastructure increased accordingly. Companies consolidated ownership of large mining regions, funding deeper shafts, more extensive tunnel networks, and increasingly complex surface-to-depth mechanical systems. The economic logic was straightforward. Deeper mining meant access to previously unreachable reserves. Those reserves represented profit, fuel security, and industrial expansion. The risk was acknowledged but calculated. What was not fully understood was how rapidly risk scaled with depth. The machine did not resemble excavation as it had once been understood. It did not dig in the sense of hand tools striking stone, nor in the rhythm of human labor measured by fatigue and repetition. It advanced through resistance as a continuous mechanical intrusion, steady, forceful, and indifferent to interruption. At its core was a reinforced drilling assembly housed within a steel framework designed to withstand sustained pressure from every direction. The structure itself was not light. It was mass-concentrated into function. Thick metal housing, layered supports, and internal bracing designed to prevent collapse under the shifting weight of the earth. Its size varied depending on application, but in its fully developed industrial form, it could extend several meters in diameter at the cutting head alone. The machine's body followed behind, segmented into connected sections that allowed limited flexibility while maintaining structural rigidity. Power came from external steam or early combustion systems transmitted through reinforced shafts or tethered mechanical lines. There was no independence in the modern sense. The machine remained bound to surface infrastructure, receiving energy, fuel, and mechanical control from above-ground systems that dictated its operation. At the front was the cutting face. This was where resistance met force directly. The head rotated under sustained torque, fitted with hardened metal teeth arranged in radial patterns. Each rotation pressed these edges into rock, clay, or compacted mineral layers. The motion was not fast. It did not need to be. The force came from sustained pressure rather than speed. Every contact produced fracture. Stone did not yield cleanly. It shattered in uneven breaks, producing fragments of varying size that accumulated around the cutting chamber. The machine did not pause to interpret these conditions. It continued forward, grinding through material regardless of variation in density or composition. Behind the cutting face, an internal removal system operated continuously. Broken material was collected by mechanical scoops or early conveyor-like mechanisms, depending on the design. In some systems, rotating screw transports carried debris backward through the machine's body. In others, chain-driven buckets lifted material toward rear discharge points. The objective was constant clearance. Without removal, the machine would become trapped in its own output. Airflow within the system was equally critical. As the machine advanced deeper underground, oxygen levels became unstable. Ventilation had to be maintained through forced air systems delivered through pipes or ducts connected to the surface. These systems pushed fresh air forward while extracting hazardous gases generated by disturbed geological layers. Methane pockets were a constant risk in coal-bearing strata. When encountered, they did not behave predictably. Some dispersed slowly. Others accumulated in enclosed pockets until disturbed by mechanical contact. In poorly managed systems, ignition sources from friction or heat buildup could trigger combustion events within confined underground spaces. To reduce this risk, components were often cooled through water circulation systems or insulated to minimize heat transfer into surrounding rock. But insulation had limits. Every mechanical interaction generated heat. Every rotation, every fracture, every pressure point introduced thermal and structural stress into the system. The deeper the machine progressed, the greater the surrounding pressure became. Rock layers above exerted downward force measured not in static weight alone, but in shifting geological stress. This pressure did not remain uniform. It changed with composition, fault lines, and subterranean voids. The machine had to adapt continuously without stopping. Its frame absorbed vibration from all directions. Reinforced joints distributed stress across multiple structural paths to prevent localized failure. Without this distribution, single points of weakness would collapse under sustained load. The cutting process itself created a rhythm, but not a human one. It was repetitive, mechanical, and unbroken. Each rotation followed the last without deviation. Each fracture of rock was identical in function, though not in shape. The machine did not distinguish between types of material beyond resistance levels. Harder layers slowed progress, softer layers accelerated it. But neither altered the method of operation. Illumination was minimal. Deep underground, natural light did not exist. Early systems used oil lamps or gas-based lighting integrated into the machine's structure. These sources provided limited visibility, often only enough to confirm mechanical function rather than environmental detail. Much of the machine's operation was therefore indirect. Operators remained at the surface or in intermediate control stations, interpreting mechanical feedback through vibration, sound transmission, and pressure readings. A change in tone could indicate increased resistance. A shift in vibration frequency could signal structural imbalance. Sudden mechanical irregularities suggested obstruction or collapse risk ahead. These signals were not precise. They required interpretation under uncertainty. The machine itself did not see the Earth. It reacted to it. Its forward motion was driven by torque applied through reinforced drive shafts. The cutting head did not decide direction independently. It followed preset alignment, adjusted only through surface control systems that modified trajectory incrementally. Even slight directional changes required careful recalibration. Underground deviation was dangerous. A misaligned path could intersect unstable geological zones or flood-prone cavities. Stability was maintained through continuous correction. The machine advanced in segments of controlled pressure rather than free movement. Each advance was a negotiation between force applied and resistance encountered. Behind it, structural supports were often installed as it progressed. Timber or early metal reinforcement systems were placed to prevent collapse of excavated tunnels. This created a dual process: excavation forward, stabilization backward. The machine did not leave empty space, it left engineered voids. Noise within the system was constant: deep grinding, metallic strain, rock fracturing under pressure. These sounds were transmitted through both the machine and surrounding earth. Operators often described feedback through vibration rather than direct sound, as underground acoustics distorted conventional hearing. Smell was also present within confined systems. Disturbed minerals released sulfur compounds and metallic dust. In coal-bearing formations, organic gases added sharp, heavy odors that lingered in enclosed air systems. Every aspect of operation confirmed one fact: the machine was not working in an open environment. It was working inside resistance. Maintenance was constant, but limited. Components exposed to cutting stress degraded rapidly. Teeth on the drilling head dulled or fractured under repeated contact with dense rock. Internal transport systems became clogged with debris. Cooling systems strained under thermal load. Repairs often required partial withdrawal or temporary cessation of operation, but stopping carried its own cost. The deeper the machine progressed, the more difficult restarting became, due to accumulated pressure and environmental instability. This created a similar logic to other industrial systems of the era. Continuous operation was preferred over interruption, even at the cost of accelerated wear. The machine therefore existed in a controlled imbalance. Too much force risked structural failure. Too little force halted progress. Too fast created instability. Too slow reduced economic viability. It operated at the threshold between effectiveness and collapse, and that threshold shifted constantly depending on geological conditions. As it advanced, it encountered more than just material resistance. It encountered voids, unexpected cavities within the earth where structural support suddenly disappeared. In these spaces, pressure redistributed violently, sometimes causing partial collapse or sudden shifts in surrounding rock. The machine's structural design had to absorb these changes without transmitting failure upward through its system. Despite its mechanical strength, it was not immune to environmental unpredictability. It did not conquer depth. It negotiated with it under constant strain. And every meter it advanced carried the assumption that conditions ahead would remain within survivable limits, an assumption that was never fully guaranteed. You do not work at the cutting face anymore. No one does for long. The machine enters where the earth is no longer stable enough for human presence, but it still depends on you. Above it, around it, behind its systems, feeding its direction, correction, restraint. The danger is not removed. It is displaced. You learn quickly that distance does not equal safety. The vibration still travels upward through the structure. A change in resistance below is felt in the steel frame above as a subtle shift, a tightening in the machine's rhythm. It is never loud at first. It begins as a variation in tone, a hesitation in motion, a pressure that should not exist in a system designed for continuity. And then it becomes something else. A collapse underground does not announce itself with clarity. It arrives as a failure of expectations. The machine advances, and suddenly, it does not. The cutting head meets void instead of stone. The support behind it loses stability. Weight redistributes where it was never meant to go. The Earth responds faster than any correction can. When structural failure occurs at depth, it is not a single event. It is a chain. Rock shifts into empty space. Supports buckle. Pressure concentrates into points that cannot hold it. And the machine, designed to push forward, becomes trapped in the consequence of its own progress. There are incidents where entire sections of excavation collapse around the system. The machine does not break immediately. It is crushed slowly, unevenly, as surrounding strata settle into the space it created. Recovery is rarely possible. When it is, it comes at enormous cost. There are other failures, less dramatic, but equally final. Gas pockets ignited by friction or heat accumulation. Methane concentrations released by unexpected geological disturbance. Ventilation systems overwhelmed by sudden changes in underground flow. In these moments, the machine does not cause destruction alone. It becomes part of a wider instability that spreads through the mine. Above ground, the effects are recorded differently. Production loss, structural damage, system interruption. But underground, the language is different. It is silence where there was motion. It is absence where there was direction. Workers assigned to monitor and control these systems live in a constant state of delayed consequence. You do not see the failure when it begins. You hear it afterward, through reports, through vibration patterns that stop, through systems that no longer respond in expected rhythm. Some failures are survivable in theory. In practice, survival depends on distance, timing, and chance. Most are not close enough to escape. Heat becomes another form of risk, though not always visible. Mechanical friction deep underground generates localized temperature increases. When systems overheat, materials expand, warp, and weaken. A component that held under normal conditions becomes unstable under prolonged strain. Cooling systems attempt to manage this, but underground conditions are unpredictable. Water delivery is limited. Circulation is uneven. Thermal balance becomes a continuous negotiation between input and failure. You begin to understand that the machine does not simply dig. It alters the environment around it faster than the environment can stabilize. Entire sections of Earth behave differently after it passes. Rock that was once stable becomes fractured. Pressure that was once distributed becomes concentrated. The act of excavation is also an act of structural transformation, and that transformation does not reverse. Workers rotate through shifts above ground, but the psychological weight of what happens below does not rotate with them. It accumulates. The knowledge that depth increases risk without visible warning creates a persistent tension in every decision. Maintenance teams examine components after retrieval, often finding damage patterns that reflect conditions no one directly witnessed. Fracture lines in metal that indicate sudden stress. Heat discoloration that reveals prolonged overload. Wear patterns that suggest forces applied from directions not anticipated in design. The machine records its own history in damage. As systems scale, fewer people are required in direct contact with the deepest zones. Mechanization reduces exposure, but it does not remove consequence. It concentrates it elsewhere. Control rooms become centers of indirect responsibility. Decisions made through instruments, pressure readings, and mechanical feedback loops determine the behavior of something operating far beyond direct human reach. A miscalculation is not immediately visible. It becomes visible later, in collapse reports, in halted systems, in sections of mine that cannot be safely re-entered. Replacement of earlier excavation methods with deeper mechanized systems does not eliminate danger. It changes its distribution. The body is no longer the primary point of failure. The system is, and when the system fails, it fails at scale. Over time, new engineering approaches emerge in response: reinforced tunneling methods, improved ventilation networks, more precise geological mapping before excavation begins. Machines are refined to respond faster to environmental feedback, to reduce blind advancement, to avoid known instability zones. But unknown zones remain. They always remain. Eventually, newer systems begin to replace the earliest deep excavation machines. Rotary tunneling systems become more controlled. Hydraulic and later electrically driven excavation tools allow for finer adjustments and reduced structural shock. Automation increases, reducing the number of humans directly exposed to underground environments. The original machine does not disappear because it is defeated. It disappears because it is outpaced. More precise systems emerge. Safer systems emerge. More monitored systems emerge. But they all inherit the same foundation: the assumption that the Earth can be entered, shaped, and stabilized through sustained mechanical force. What remains behind is not just abandoned equipment, but altered geography. Tunnels carved and later sealed. Cavities reinforced and forgotten. Underground pathways that no longer serve active purpose, but remain structurally present beneath industrial regions. In some locations, remnants of early deep excavation systems remain preserved in fragmented form. Rusted frameworks embedded in rock, reinforced shafts now sealed, machinery components partially encased in sediment, visible only through controlled access or accidental discovery. They do not function anymore, but they do not disappear. The legacy of the machine is not measured in its operational lifespan alone. It is measured in the change it introduced, the acceptance that human reach into the Earth would no longer be limited by strength, but by engineering tolerance for risk. Modern excavation inherits this condition. Even with advanced systems, monitoring, and predictive modeling, the fundamental problem remains unchanged. Depth introduces uncertainty. Uncertainty introduces risk, and risk scales with scale. The deeper the work goes, the less control becomes absolute. The machine that once dug too deep did not solve that contradiction. It revealed it. And what it revealed still governs every attempt to go deeper than before. Because beneath every layer of improvement, every refinement of technology, every reduction in direct human exposure, the same question remains buried in the structure of the work itself. How far can something go into the Earth before the Earth answers back?